Hello and welcome. Um, this short video provides an overview of a study by Nagpal et al. Called Deep Learning for Face Recognition, Pride or Prejudiced, where the authors investigate the underlying causes of bias observed in facial recognition systems, in particular as it relates to racial and age-based bias. So we've got 4 slides. Myself, Korsno Vapana, will present the first 2, at which point we'll hand to Tebelo Labesa to present the second 2. The authors start off by pointing out or speaking to 2 incidents, concerning incidents of bias observed in production grade facial classification systems. The first is the unfortunate case of an African American couple who had their selfie classified as gorilla by Google's photo classification system. The second is Amazon's recognition system designed to classify individuals as criminal or not, which when applied to members of US Congress resulted in a 40% greater probability of classification of African Americans as criminals. And so subsequently, both of these incidents highlight that even in top class systems, that in-group biases may be present. And so until this point in time, there hadn't been a systematic analysis of the underlying causes of these biases in these deep learning networks. And so subsequently, this is really the focus of the authors in this paper, is to understand how these networks are encoding facial information, to ultimately understand how these biases and misclassifications are emerging. And so they do so by understanding how networks encode both age and race-specific information. 4 bullets in terms of their approach. So the authors evaluated 4 deep learning networks that are well suited to facial recognition and classification, being Light CNN9, Light CNN29, ResNet 50, and SenNet 50. The authors made use of 2 groups of data sets. So the first was for the analysis of racial biases, where there were 3 data sets that were made use of, and the second was for evaluating age-based biases, where there were 2 data sets made use of. So both of these essentially are input images and associated labels. So in the case of race, what is the race of the individual in the image? In the case of age, what is the age of the individual in the input image? And so 36 experiments were conducted, essentially combining different networks with different data sets and different training regimes. So for example, in race, they would evaluate a network that is trained on balanced data that has representation across all the racial groups, to evaluate how that information is encoded. They'd also do so training the network from scratch with only one racial group, or for example, fine-tuning a network with one racial group after it was trained with a balanced set, to temper out differences in how the network is encoding the data. And so subsequently, each experiment was evaluated in terms of the extent of the bias, looking at verification accuracy, and then the underlying cause of misclassification was assessed through activation maps and feature visualizations. And that's really the second bullet there in terms of the evaluation, is the focus of this paper. And so the core finding, I think, speaks to the fact that networks trained with different races result in different encodings in the network, and that this is an indication of bias. And so on the right-hand side are a set of feature visualizations. This is an area that the authors explored. Essentially, the final convolution layer is interpolated and then superimposed on the input image to understand the different regions of focus or features that the networks are focusing on based on their training regime. And so highlighted on the left-hand side is ResNet 50 when trained with balanced data. So the first row, race A, refers to caucasoid and race B to congoid. And we see that when it's trained with balanced data, there is, I suppose, a union of salient features that the network is focusing on. Whereas on the far right-hand side, when the network is fine-tuned using a specific race, the areas of focus change quite drastically. And so in terms of race A, you fine-tune the network with caucasoid data, and then it results in a focus on features around the eye region. And for race B, the bottom right-hand side, when you fine-tune the network using congoid data, instead the features around the nose, lips, and cheeks are the focus areas. And so this ultimately indicates that imbalance in the training data is represented in the way that the networks are encoding this data, which is subsequently the underlying cause of the bias or misclassification. The authors also highlight that the findings of the study are quite parallel to what we observe in neurocognitive literature. The features that are highlighted in the fine-tuned networks are the same features that people in these racial groups use when describing and identifying other people. Another like finding is that the existence of in-group bias in society is largely driven by a lack of exposure to individuals of other races, which is essentially a very similar underlying cause of shifts in the focus of the networks in terms of the features and the regions of focus.
Thank you, Christian. My name is Tebello Lebesa, and I'm going to do the next two slides. Okay, so here we have the contributions of the paper, and it's very important to note the context in which it was drafted. The data sets used for the research were unbalanced in an attempt to simulate the real-world situations where the data available is more representative of one group than the other group. And then the researchers were also trying to find out if deep learning models had own race or own age traits that are existing in human beings based on the data used to train the models. Okay, so there are four contributions made in this paper. Deep learning networks tend to be biased in terms of race and age, depending on the training data it was exposed to. The networks are also similar to human behavior in that they encode specific facial regions based on race and age during the training process. So what it does is it learns specific facial features depending on the input, on the race of the input images. Okay, so using pre-training models on large-scale data with varying distributions can also be beneficial, even though age remains a huge challenge. Okay, so now moving on to the next slide. This last slide shows the implications of this study for artificial intelligence and natural language processing. We have 5 implications of the study categorized in 5 different themes, and I'm just going to summarize all the implications. Okay, so as we've seen, neural networks can replicate human biases. It is important that researchers reevaluate their algorithms to ensure that they are unbiased. Pre-trained models tend to be more biased, but there are suitable cognitive techniques that can be used for debiasing on pre-trained models for better usage. Okay, so there is a solution for that. And then training data should be inclusive of all groups or classes to avoid in-group biases. Okay. And it's also important to understand the way deep learning networks encode information to detect if there are any biases introduced by the models. Okay, and then the last one is that all models should be tested before deployment to ensure that systems are unbiased and fair. So to conclude, striving to build unbiased systems will ensure that AI benefits all groups of society, and applications can be used without in-group discriminations that are existent in human beings. Thank you.